Hello everyone, my name is Paulina Tomaszewska and I'm a PhD student at Warsaw University of Technology, Poland. Today I would like to present the work that I did under the supervision of Professor Christoph Lampert from the Institute of Science and Technology, Austria. The title of our work is Lightweight Conditional Model Extrapolation for Streaming Data under Class Prior Shift, in short, LIMES. The work was already presented at the International Conference on Pattern Recognition last year. But before I start, let me give you some food for thought and ask you a question. Have you ever struggled to build an accurate model when dataset was highly imbalanced? I guess most of you had such a situation. But now, let's make it even more difficult. And imagine now that the class imbalance changes over time. This is actually the scenario that I tackle with in the paper. So now, as the title of the paper is quite long, let me divide it into two parts. And first, focus on the second part, so on streaming data and the class prior shift. Streaming data undergo many different changes. And here we have 4 visualizations that will actually simplify maybe a bit the topic. So first we have our original data, the visualization on the left. And we can see 7 red dots and 8 green dots. And the dotted line signifies the decision boundary for the classifier. First of the changes that may happen is called real concept drift, where the class distribution changes so that the decision boundary is also changed, because the conditional probability of y given x is different. Another change that we may see in the data is called virtual drift. Here, the probability of x changes, but the boundary, the decision boundary is the same. And the fact that p of x has changed here is shown by the change of the location of the dots. And the last change that I'd like to talk about is called class prior shift. Here, the probability of y changes. It is shown here by the fact that the ratio of the red dots to the number of green dots has changed. Initially it was 7 to 8, and now it's 2 to 5. And as a consequence, the decision boundary can also be changed. And in this presentation, I will focus only on the class prior shift. Okay, we know that data can experience and undergo some changes, but how actually we can address this problem when designing the classifier? Here there are 3 possible approaches. The first one is that we have one model that will work well on average, because there's no adaptation. The other approach is that we have a pool of different models, and once the data is arriving and we know what kind of scenario is this data representing, we can pick the right model from the pool. But in this case, we need as many models in the pool as the number of scenarios that we think that we're going to experience. And the last approach is that we have one model that can be easily be adjusted to different scenarios, so to different class distributions. And this is the idea that we use in the LIMES method. Please note that LIMES is better than the first approach, because still we have just one model, but that is flexible so that we can adjust it. And it's better than the second approach because we have one model instead of a pool of models. So we can say that this is kind of concatenation and actually a mix of these 2 first approaches. Okay, so now let me focus on the first part of the title, which is lightweight conditional model extrapolation. Okay, so actually how the idea for the LIMES came up. So the inspiration was from the meta-learning field, where the mammal solution was introduced. And in this approach, we have a model that can be easily adjusted to different tasks, so that we have one set of weights that can be adapted to different tasks by applying some few gradient updates. In many cases, just one gradient update is enough. And LIMES is similar, because we also have a set of weights that are going to be adjusted and modified for the specific case. But in this case, we don't need any gradient updates. We just apply the analytical formula. Okay, so now what's actually the goal of the paper? So we have a model that was trained on data from P distribution. The model is called F, so that we have the input, and we want to predict the values that are as close as possible to the values from the distribution P of y given x. So this is the model F. And we want to apply the knowledge, actually, that is within the model, it's already trained, and apply it to the data from the Q distribution. So you want to somehow shift the model F so that it will be appropriate for the new distribution. Okay, so now let me move to the core slide from this presentation. So to the slide about classifier adaptation and the derivation of the analytical formula. That is the key element method. But before I will move to the part where we derive the formula for the adaptation, let me briefly describe the assumptions that we made and that actually reflect the fact that we analyze class prior shift. So we have the original distribution, which is called P, and the new distribution, which is called Q. And we want our classifier to move from one distribution to another distribution. And the first assumption is that the probability of y is different in the case of P distribution and in the case of Q distribution. This is the first thing, and this is actually the main idea behind class prior shift. And the second assumption is that the conditional distribution, conditional probability of x given y is the same in the two scenarios, so in the case of P and Q distribution. And this second assumption we're going to use in a moment once deriving the adaptation formula. Okay, so now let me move to the first formula on the slide. What we want to do is that we have our classifier that we hope that output the values as close as possible to the true conditional probability P of y given x. So we want to know how to map these values of P of y given x to the values of Q of y given x. So we want to find the mapping. And once we know the mapping on the probability level, we can apply it to the classifier itself. So we have here, what we do first is that we have the conditional probability of y given x in this Q distribution. And we apply the Bayes rule. So we rewrite this conditional probability. Once we have it done, we apply the class prior shift assumption, the second from the green box on top. And then the last step is that we once again apply Bayes rule, but on the conditional probability from the P distribution. And then we achieve the final version, the one that we have on the right. But please note that some terms here are in red color. It means that they do not depend on y, and this is why they are irrelevant for the adaptation process, and we can simply omit it. Okay, so we know now how to map one conditional distribution to another one. Okay, but now how actually use this information when designing the classifier. So a small recap now on how the classifier output with softmax layer on top looks like. So we can say that the output of the model is proportional to the exponential function on the linear combination on the input values to the last layer. And hopefully this formula is as close as possible to the true distribution of P of y given x. So now we can combine the information from the first and from the second formula and create on the classifier that would hopefully mimic the true distribution Q of y given x. And we can see that this is proportional to the same exponential function as in second formula, but this is multiplied by the factor of q of y divided by p of y. And this factor we can move inside the exponential function, so that within the exponential function we have this plus cy term. And the cy term is called bias correction term. And what this bias correction term actually means, I will now try to decipher. Okay, so this bias correction term that is visible now in this formula on the top, it is actually the difference between the two logarithms. The logarithm of the qy minus the logarithm of py. Whereas the qy is this new distribution and the py is the previous distribution. And this previous distribution, we can think of it as a reference class distribution. And so that this is a reference point that later on we can move to any other distribution, any other point. And so it is useful to think about this reference class distribution as a uniform values over all classes. Okay, so this is the end about this theoretical part, the derivation of the Limes method. So now let me move to the empirical part, where we conduct some experiments to actually verify whether Limes achieve superior results to other methods. So we decided to use Twitter data, as there's a lot of it and it can serve as streaming data. So the goal is that once we have the data in the form of the text of the tweet and also some metadata, we want to predict the country where the tweet was issued. Moreover, we want to train a model in a continuous manner, so that we have streaming data where the data is in the right order and we use each sample only once. And also the model should be lightweight, and this condition is met because we have just one model instead of a pool of models. Okay, so let me begin with actually explaining a bit about the data set, because we know that everything starts with data. So we collected the data using Twitter's streaming API. The data was from April to July 2020, and there were in total 250 countries as classes, and we consider countries not only the ones that are independent, but also the ones that claim that they are nation. And the training data, here we created two different subsets. The one was called early and the other one lately. In the early case, the data was from the 1st to the 5th day of each month. And in the case of lately, data was from 11th to 15th day. And as we had a lot of data, we decided to split the early and the lately subsets further, and so that each of the subsets actually later on was split into 10 realizations, because we want to have many models trained on different subsets of data, so that later on we could compare the results and apply some statistical tests to analyze whether the differences are actually meaningful and significant. And so we wanted to increase the credibility of the results. Moreover, we decided to create even more variants of data, so that in some experiments we use only text of the tweet as an input. In other experiments we use the information from the location metadata field. But please note that this location metadata field was a plain text, so actually anything could be there. It's not that someone just picked up from the list a particular name of the country. And in the last scenario, we concatenated both data sources, so both the tweet and the location metadata. The data set that we created was made publicly available, and this is available at the website, and this is in so-called dehydrated version, because we couldn't make publicly available the raw data, but still the original data that we use could be recovered based on the information that are on the website. Okay, and as I said, we use Twitter data, but some of you may ask where actually the class prior shift happens in case of this data. So it is shown at the figure on the slide. So here we have the class distribution across 24 hours for 5 most frequent countries. And what we can see is that at the beginning of the plot, most of the tweets come from US and Brazil. This is the same at the end of the plot. However, in the middle of the plot, we can see the drop of the number of tweets from US and Brazil, and increase of the tweets from Great Britain. And this is attributed to the fact that we have different time zones, so that once some countries tweet, the others sleep. And this fact makes the task of predicting the country where the tweet was issued more difficult at some times and easier at the other times. So now let's make the task maybe more formal. So the task of the classifier is to perform predictions on data from our T after having experienced the previous data, so from 0 to T-1 hour. And the training should be in a continuous manner. So the idea is that we have a reference distribution and we want to move to different scenarios. But first of all, at time T. So in this case, our bias correction term looks like this. We have the difference of the logarithm of the class distribution at time T minus the logarithm of the class distribution is the reference one. And here comes the problem, because we don't know what is the true class distribution at time T, because we get some few samples from our T, but this is not sufficient to estimate what will be the class distribution from the whole records that are going to come within the hour T. This is why we need to apply some additional step called extrapolation. And here the idea is that we want to search for the information within our lookup table, where we store the historical class distributions. So we know what class distribution we have just experienced a moment ago. So from the hour T-1, because we have seen whole data, all the records from this hour, and we can calculate the true class distribution. And the idea is that we are going to search in our lookup table the class distribution that was the closest to the one that we experienced at our T-1. And so once we find it, we denote this class distribution that this is the one from the time T star. And then we take the class distribution that happened just after the time T star, and we hope, and we actually assume that this class distribution at time T star plus 1 is going to be the most similar to the class distribution at our T. This is the one that we take and apply to our bias correction term formula. Okay, so we now a few words about the implementation of the system. So first of all, we downloaded data from the Twitter. Then we extracted the needed information. First of all, the text of the tweet. And then we wanted to create the embeddings of the text. And here we applied the pre-trained sentence transformer, which is suitable for social media data. And once we apply it, we achieved the embeddings of size 512. Having this data, we simulate data stream so that we use the data in chronological order, and we used each tweet only once. And this was the input to our classifier with the ability to adjust to different scenarios. And this is the LIMES method that I described. Please note that the setup is analogous to linear probing, because the step with the generation of embeddings is fixed, and this is done only once, and this is not a trainable step. We only focus on the classifier itself, so on the LIMES method. Okay, as I mentioned, we wanted to compare LIMES against other baselines. And here are the baselines that we introduced. There are 4 of them. So the first one is called incremental. And this is the method where we train a model in an incremental way, but there's no bias correction term. So this is a similar setup to the first method that I explained once I was talking about possible approaches when dealing with streaming data, undergoing some data drifts. The other approach is called random, and here it works in the same way as LIMES, but here we don't use the extrapolation step, so that we don't search for the most probable class distribution that may occur at time T, but instead we take just the random historical class distribution. The other approach, the other baseline that we analyze, is called ensemble. Here we have 24 hours, each dedicated to a particular hour, and each model is trained in incremental manner. We have 24 models because we assume that this is the natural cycle within our data, And we can say that this approach is similar to the idea with the pool of models, that we have many models and we pick the right one for a particular moment. And the last baseline that we have is called restart. And here the model is trained only on the data from the previous hours. And this model is used for the evaluation on the data from hour T. And now let me move to the most interesting part, so to the results. And here we have shown 3 charts on the top. We can see the one with the values of accuracy per hour for the 5 analyzed models. Here we have the model that was trained on only the text of the tweet, and we use the early subset. And please focus now on the 2 curves, so on the blue and orange one. The blue corresponds to Lime's method, whereas orange one to the incremental. And we can see that the 2 lines are close to each other, but the biggest difference where Lime's method outperforms incremental, so the blue one is above the orange one. These are the cases where we have the valleys on the chart. And please see, for example, the moment of hour 56. And here we can see this gap in performance where Lime's outperforms incremental. And the valleys are the moment where the task is the most difficult. And here Lime's is better. And it means that the fact that we applied bias correction term, which was not used in the incremental method, actually matters and brings benefits when it comes to the performance. And please also note that the lines which corresponds to Lime's and random methods, so the blue and the green ones. Always the blue is above the green one, and it means that the fact that we applied extrapolation step instead of taking the random class distribution is once again important, because otherwise in the random method we introduce additional bias and noise to the model, and the model performs worse than it could when this class distribution would be chosen carefully. So these are the results once we analyze them per hour. We can see that the other methods called ensemble and restart are much worse than the Lime's incremental and random methods. But actually sometimes it's difficult to analyze the results once they are so detailed, and it's better to aggregate them. So this is what we did on the charts below. And we have 2 variants. On the left, we have calculated the average per day accuracy, and on the right, the minimum across day accuracy. And what we can see on the left is that Lime's outperforms incremental always, but this difference is very small. And it makes sense because, as I said, incremental method uses only one model that actually in the end works well on average. And this is what we can see here, because there's no adaptation step. And this is the result. On the right, we can see the case where we analyze the minimum across day accuracy. And here, this is we can see a significant difference between Lime's and incremental. Here, Lime's work much better. And this is attributed to the fact that Lime's, instead of working well on average, is able to adjust to different scenarios, even to the most difficult ones. And let's move forward. So we not only analyze the results visually, but also a more detailed way. And here we have 6 variants, because we had 3 different data sources. So the tweet location and tweet plus location. And also we had 2 different subsets. So the subset early and subset lately. And here we aggregated the results from 10 realizations. And we have 2 columns in each table. We have average and minimum. And average is actually the average of the average accuracy per day. And minimum here is the average of minimum accuracy across day. And what we can see is that always Lime's outperforms other methods, but the difference in performance changes, so that once the task is the most difficult, because we use only the text of the tweet as the input, then the difference is the biggest. And in the case where we use both the tweet and the location metafield, then the difference between Lime's and the incremental method, which is the best among the baselines, is the smallest. So this is an important highlight. But please note that the differences between the models are statistically significant in all cases, and it was checked using Wilcoxon statistical test. And now let me move to the last slide, which is about the conclusions. So in this talk, I presented the LIMES method, which is general and lightweight. It is inspired by meta-learning approach. It consists of two mechanisms. There's bias correction term and extrapolation that is happening within the bias correction term. We applied the method to Twitter data, and we show that LIMES outperforms other baselines, especially in the case of real-world scenario, the real-world metric, which is called minimum across the accuracy. Also, it was shown that the more difficult the task is, the bigger the gain affects the use of LIMES. That's all. Thank you very much for your attention.